Hello, everyone. My name is Pankaj Gupta, and I work for AMD in Linux kernel and virtualization group, primarily on confidential computing. And I've been working on uh, Linux kernel and virtualization from last more than 10 years. So today I will present on SNP Live Migration with guest-memfd and mirror VM. The agenda of my talk, first I will introduce the basic concepts, live migration and primarily SNPs, the approaches which we are taking for SNP live migration. The apparently two approaches, one is the mirror VM and another one is shadow vCPU. Current challenges which we are facing with these approaches, and we'll also talk about the common vendor abstractions and SEV SNP specific tasks which we list on and needs to be worked on. Uh, First, I will introduce the AMD SEV SNP, which Tom also explained in detail in yesterday's his talk, and Paulo also touched. So this provides SNP provides the VM isolation and integrity protection for guest VMs, as VMs will have their own symmetric keys and encrypted encrypted with their unique keys, and all the VMs and hosts are encrypted with their corresponding keys. They cannot see the encrypted text of each other, and SNP provides the integrated protection where the guest memory cannot be remapped or replayed or corrupted to avoid these attacks. So this is done with the help of SNP extensions in the hardware and of course the software support. The traditional virtualization used to work is we used to do the emulation in the VMM user space and in the VMM user space, and since with SNP host is considered as untrusted, so it cannot access the VMM memory. So we have to do the emulation, either we have to move the emulation either in the hardware or in the VM address space or VM context itself, so that yeah. So for that we also have these hardware extensions which we call as VM privilege levels, and these VM privilege levels provide access protection for the VM memory at various levels, like VMPL0 being the highest privilege level and VMPL3 is the lowest privilege level, and we do the emulation of some of the highest privilege devices on VMPL0, example VTPM, and other privilege operations, example memory acceptance, which is an important step for SNP, which we do at VMPL0 level. And since we for live migration we want a mechanism which can copy the VM memory, and we are also doing the live migration inside guest context at VMPL0. That's the place where SVSM runs. SVSM is a secure VM service module, which is a Rust-based module, which provides all these infrastructure and is developing very fast. And for this, so we plan to use the SVSM to do the live migration packaging and other things. Another important point is this VMPL address sharing or restrictions for address level is restricted by the hardware itself. So in the diagram, you can see SVSM runs at VMPL 0 level, and we have guest OS at VMPL 2, and then normal KVM and QEMU in the host side. SNP Live Migration, as Live Migration, we know that moving a running guest from one host to another, it could be same host or another host. But with SNP, we want to maintain the SNP security guarantees while doing the live migration to avoid any of these attacks, which we listed for confidential VM specific to SNP. And since we have no guest memory being only accessed at guest address space, so we want this to be controlled from the guest side. We cannot use the normal vCPU's time to do this live migration, so we need additional vCPUs to do the live migration, because if we steal some time from the normal vCPUs, it will slow down and the effect would be visible. So we need the mechanism which we are going to discuss will require additional vCPUs which run at the guest context and doing the live migration. So these vCPUs will be doing the memory packaging, which is the encryption and hashing together. We'll talk about this. Yeah. For this, two techniques we are considering. First one is the mirror VM technique, and other is the shadow vCPU. And as I said, both these techniques use additional vCPUs, and but the way they create these additional vCPUs is a bit different for both these approaches, and we will see them in coming slides. But only common thing is these additional vCPUs or vCPUs run at VMPL 0 or at the level of where SVSM or Coconut SVSM, which is a current working module, runs. So these vCPUs, additional vCPUs, will not be exposed to guest OS and will only be running at SVSM level. First technique is the mirror VM technique. The mechanism which mirror VM use is it uses a different KVM object and then the primary VM, and it creates these new vCPUs in the context of this KVM object and runs at SVSM layer. Yeah, so it just divides it just reduces the data structures per KVM level, and there's not much sharing on the common data structures like Epic and all these things. And the dirty bit tracking is done at the host side. And yeah, SVSM does the memory packaging, and so only difference is it uses a different KVM object, but it also, this first mirror vCPU is created as the live migration starts, and we currently spawn the mirror vCPU on this mirror VM when we start the live migration from the QEMU process. And if we need more mirror vCPUs, we can spawn it on demand and just to scale the live migration. And these mirror vCPUs are dedicated only for live migration. They go to the guest VM context at SVSM layer, then come back and do the task of packaging and transferring the memory, encrypted memory. So we tried with the mirror VM approach, as this is the feedback we had from the maintainers, and we found out that the mirror VM currently doesn't support the address space sharing between primary and mirror VM. So by address space sharing means right now, sorry, I meant mirror VM with guest-memfd. So those guest-memfd is a new interface which got added recently in the Linux kernel and KVM space, where earlier we used to, the QEMU process used to have the memory in the user space, address space, but now with guest-memfd, the memory is stored in the Linux page cache with direct from KVM interface, file map interface, and there's no involvement of user space doesn't have memory with it, the private memory, I mean. So this is guest-memfd, but the current state of guest-memfd is it works with the single KVM object. But if we have the primary KVM object and the secondary mirror KVM object, which can simultaneously work on same memory backend, so we don't have that support yet, as it's based on single KVM object. And we need some sort of sharing between both primary VM and mirror VM, because to work on this memory for the mirror VM, and we need some mechanism, like if mirror VM is packaging this memory, like importing or exporting, importing in source and exporting in source and importing in destination. The primary VM would also be working in this memory, so we need different memory view for other operations, like if this memory is faulted on the primary VM or some other operation happened. So this support is not there, and we need we need something like VMA like memory sharing, not exactly VMA, just as we don't have VMAs with guest-memfd, but we need some sort of mechanism, example to memory attributes, but with different memory views, example for primary and mirror VM. So there is a patch series. We raised this little bit of this concern with our maintainers upstream, and there's also a patch series present which allows us to access the list of GMEM pages from multiple KVM objects, but this doesn't provide currently the simultaneously or parallel access of the memory from KVM object, or this needs to be tweaked a bit if it gets going. I need to look it more in deeper, and we also had discussions in past few days about KVM Forum for the support of multiple KVM levels, which I suspect needs something similar when we had the discussion with VTL people. And Paulo and Sean had good suggestions how we define those interfaces. So I want something to be added on these things for mirror VM if we go with this approach. So I need inputs on this, how we can make it functional based on what we need currently. So alternate approach which we are considering is we want to we are spawning additional vCPUs which we call shadow vCPUs, and these shadow vCPUs just add into the QEMU address space on the same KVM object, and as you can see the dotted line, they are only visible till VMPL0 SVSM layer. They don't need the multiple, as they share the they share the KMO address space, and they don't need the multiple KVM handling with guest-memfd, and they also can work together on the memory while and do the live migration. So in this case, the primary VM itself does the live migration, and AP creation, the creation method of these vCPUs is done with the dynamic VMSA creation. But this also has, after mirror, I faced problems with mirror VM. I went to this shadow vCPU thing, and we need, and I'm adding these vCPUs dynamically, as there was some suggestions in the past from maintainer, and I added these when we start the migration. So we need some non-overlapping epic ID tied to the current KVM epic object to get it working. So I need to look at that, but apparently this will use the same KVM object. So we are also looking at the common Cocoa live migration problem, and we know multiple vendors need the live migration, and these are the few problems which we are listed and want the vendors to also contribute, as these are common problems. So we in spite of defining our own interfaces which would not be compatible later with the other vendors, we want to define these vendor APIs or KVM octals before, and we had some discussions, but we need to discuss more and involve maintainers. Then the attesting, second one is the attesting the target, where VM when migrates, it should attest the target itself so that to make sure where it's migrating is fine. So the important part is integrity protection during live migration, because when we move pages from one host to another, we have to maintain the integrity protection. And this also more or less is a common problem with some vendor specific bits which can be tweaked later. And guest-memfd specific APIs for pre-migration and post-migration. Also, I see patches on post-copy live migration from James, but I also want these things to be considered based on the approach which we are taking currently, so that later we don't feel we miss something or another. So these are the common interface on which we want more collaboration across the vendors. And lastly, the SNP specific tasks which we plan to work on once we solve the initial spawning additional VCP problem and working on memory migration, memory packaging thing. For live migration, we need a way on which host and the encrypted memory transfers from source to destination. And for that, both source and destination needs to be aware of a common transport key. So we have a we have a mechanism on which we can exchange the keys using attestation from source and destination. Then the memory packaging and dirty bit logging. Host will do the dirty bit logging, and SVSM would package that memory. At the end of live migration, VMSA and other VM state transfer. And important, last but not least, is the end of live migration validation. So all these tasks are big, and they need their own handling. And I want to summarize our approaches which we are taking and where we are currently. So we started with mirror VM, and with mirror VM the good benefit instead in addition to the having separate structures like epic for different KVM objects, we also distribute the responsibility to a completely different VM. If in future we have bigger VMs, there's less opportunity of clubber things around, and at least we have a separate object-oriented model. And it also provides a better accounting for cloud providers. And so by default, separates KVM object for vCPUs in mirror VM, and we don't have to take care of this epic ID problem, which we talked about, shadow vCPU, the overlapping epic ID thing. Both these approaches also have common things which we need to work on, like creating APs. The mechanism is a bit different. The epic ID thing we have to teach to KVM, but the creation of APs from host to SVSM is a common problem we are working on. I worked on the implementation of creation of conversion of QEMU migration threads into the shadowy CPUs by using the host CPU ID based on the suggestion on the last posting, which was around 3 years back on SEV. I have the code, but it's not. I haven't tested it because I can only test once we have the shadow vCPU or mirror vCPUs going, and we want maybe for simplicity we can go ahead with the shadow vCPU thing to get this tested or other things, and parallelly look at the how things evolve for the mirror VM thing. And based on also I expect the suggestions from the maintainers and the community if we go ahead with the mirror VM approach, how we can solve the problems which we are facing currently. Only and the con for shadow vCPU is as I mentioned, is it will not have a separate KVM object, and all will be in the same context, KVM context. So these are the references which I used and can refer. And yeah, that's it. So I'm thank you for listening. I'm open for questions. Yeah.
Thanks. If I understand correctly, nothing here is really post-copy or LM specific. Are you really just asking how do we implement VMPLs? Because your plan is to do your live migration via an agent in VMPL 0, is that right?
That's right.
Okay, so are you just saying how do we do VMPLs? What is live migration specific here? Yeah, but isn't the mirror VM just VMPL 0?
It's let me yeah, okay. It's another VM which is mirror of parent VM, and it works on the same memory.
Isn't that VMPL 0?
No.
Like, no. Why not? I mean, if your plan is to put an agent in VMPL 0, it can access all of the guest memory. Why doesn't it package the memory and send it across?
So we have to package the memory, because if we, yeah, please. Yeah.
It's not the vCPUs. So it's running at VMPL 0, but it's not the actual vCPUs that are doing the migration. It is extra threads that we hoist into the VM in the same ACID so that you can run the vCPUs at the same time that you're shuffling memory over to the destination.
Yes.
Okay, it's all about running it at the same time.
Yep, yep. And so that's why it's a mirror. It gets shoved in with the same ACID. The code's in there for SEV already in KVM. It just doesn't have to deal with all the other shenanigans.
Okay.
So you only told us half of the story. What happens on the destination? Like, how do you start the VM? How do you attest that you got something that is not hacking your VM? And how do you start with the new VMSA? Because otherwise you break the attestation report of the VM on the original side. Of course, I don't expect you to go through it in the answer, but have you thought about what happens on the destination?
Yeah. So when from source, if it's a common encryption key, it will be, of course, after the attestation, when source VM will be starting transfer to destination, it will again need to attest the destination, and if it's a valid host or follows the criteria, and then the encryption key would be known to both host source and destination destination can decrypt the memory which is encrypted by VM. But of course, I think the hash key would also be known. But regarding the VM states migration, so we need to, at the end of live migration, we need to transfer those VM states, vCPU states as well, or VMSA states like VTPM states, and we have to dynamically add those into the memory context. And for that, we either need to slow down the vCPUs, or that's why we need separate memory views, so that it should not be the primary VM working on the memory and we try to do something. So we need to also slow down the primary VM also, and so that we have the entire context created at the destination and get things going. But yeah, it's a good point here.
Yeah, and also regarding what happens on when you create the mirror VM, I'm not sure I understand. When you create, you can only create new VMSAs and before launch finish, right? No, you can only create the BSP before launch finish. So there is no BSP in the mirror VM.
Right. The mirror VM wouldn't have a BSP, right? It's just going to have vCPUs that you would create. The SVSM would call an AP create and
those
create
do not end up in the measurement. Only the BSP VMSA ends up in the measurement.
Right.
So you would
with an SVSM, yeah, it would just be the BSP VMSA that's in there, and then all the other vCPUs are created by the SVSM. So you're trusting.
So basically, you have to kind of fake starting the VM with launch finish on the destination, so that you get a measurement that's valid, but then you cheat and overwrite memory behind the VM's back with data that is, of course, encrypted with all the proper protocols to ensure that it's secure behind the back of the VM on the destination, so that it can actually start. And then you basically at some point tell the SVSM, do not start normally, overwrite your VMSA with this new thing and start with this new state. Some kind of trampoline or something.
Yeah, there's also a concept in the architecture of an IMI, an initial migration image, which is a subset of the initial launch image. So you can launch, you want to launch the same thing on the destination because you want to have the same identity associated with it. And so you could either launch the exact same image that you initially measured, or you can launch a subset of it, just the pages that are marked as IMI pages, and that's still good enough.
And I think that this IMI thing may also be helpful with what Ani, Alex, and Vitaly were presenting yesterday, because then you have something that is much smaller and much less likely to have issues with the customers wanting to bring its own migration image or something like that.
So this week we've had a few questions about a network connection from the SVSM. It's been talked about for the VTPM provisioning, for instance, and this idea of, do we want a TCP/IP stack inside of the SVSM, or do we want some sort of proxy going on? So I guess my question for you is, for live migration, have you thought about what the actual mechanism for getting the pages from the source to the target would be? And is there some overlap there? Would it be going more towards QEMU's, through QEMU's existing migration flow, or would there be sort of more like an independent networking connection happening inside of the guest? Maybe there's some connection between these two different needs.
Yeah, sure. Right now, I don't see like we should have the TCP IP stack in SVSM, and how we see it is we put the packaged memory from the QEMU source to destination in the output network connection. Maybe it's, again, I don't know whether it will be TLS or something, but it's through QEMU network connection with the destination. But the memory is packaged, and we need some mechanism with which we make sure whatever is sent, of course, if it's hashed, hash should be measured in the checked in the destination, but we need to see the sequencing, or there is anything happened, abrupt thing happened in the communication with some sequencing or something. Yeah. So this is.
So I think all that is needed is some pre-shared secret for the source and destination, or an asymmetric key, where the source just encrypts everything, and then we let QEMU do its thing, transfer the memory as usual today, and then the destination knows how to decrypt it, so plug it back in. So SVSM itself does not need to do that.
So do you need some private and public key for?
Correct. Yeah.
So it will not be public-private key. It will be a secret key, transport key.
Just on the guest-memfd, if we're going to go a KVM VM per VMPL, then it totally makes sense that we need to get guest-memfd to be able to be used by multiple KVM VMs.
Yeah.
So I think that's probably the way to go. Yeah.
Yeah. Yeah. Thank you for listening. Yeah.